Smart things, like people and animals, are traveling. Think space travel, time travel. They're traveling. Dumb things, no offense, like rocks and clouds, and hopefully not you, dear listener. Dumb things are just moving. They're not traveling. Yeah, they're in motion. We're all in motion. Motion is a different word. Let's use two English words and not all three of them. Traveling is something that smart things do, things with intelligence, natural, artificial, or strategic, but we're talking about natural this week. And moving is what dumb things do, the things without intelligence. Both, smart things and dumb things, both are trapped in time and space, as far as we know, or a world that we describe with those two terms. We're trapped. We're all trapped. But smart things, things with natural intelligence to be sure, and perhaps artificial intelligence as well, smart things can travel in two ways. They can travel physically. You're very familiar with this. They can also travel mentally, whatever we mean by mentally. If we're asking the question, what's going on out there, we should be interested in travel, mental and physical. We can also be interested in motion and moving, the lesser forms, but travel. Travel is most interesting. And we're looking at natural intelligence this week. Our point of departure here at Retrace is the concept of intelligence. We started with strategic, then we went through artificial, we're into natural, and I could say we're going to go beyond, but who knows what's going to happen next week. It's just, I can't travel that far mentally in time. This is Retrace segment number 11, November 4th, a Wednesday, 2020. And I'll take this opportunity to say something I haven't been saying lately, but I should be saying it. The partial notes from today's live stream, which will become a podcast, and the chapters and the references will all be in the show description or the show notes in your podcast player or in whatever platform you're listening, or whatever platform you're listening. And then the full PDF notes will be on our website. Our website is retrace.com, retraice.com. All right. Motion versus travel. Okay, we're just inventing a distinction here, or latching onto it. Look, you can say that a billiard ball travels, that there's travel in a loose piece in some contraption. Fine, okay, but let's just say for the moment that only smart things do traveling, and then everything else does motion or moving, a lesser form. Okay, so. What do you mean? So what is it? Well, what's the difference? If there is a difference, if we assert there's a difference, if we're latching on it, what's the difference? Okay, did you say that you when you go on vacation, do you move? We moved up to the lake this summer. This year I hope to move overseas. You can't say, well, I mean, it does have meaning, right? But that means something else in that context, that you're actually relocating, which is different, right? No, you say you travel. You travel to the lake, you travel overseas, hopefully if you're fortunate, etc. Okay, so, well, what other kinds of travel do natural intelligences such as ourselves do? Well, time travel and space travel. Let's start with the second one, because obviously I've rattled your cage a little bit by saying we do time travel, but I will defend it in a moment. But no, I don't know something that you don't about the technology available to our wonderful species. Let's start with space travel. Oh, and no, I'm not going to talk about rockets and outer space. That's outer space travel, or extra terran. I don't know. Let's invent a term, or let's not. Okay, let's just talk about normal space. We travel from here to there. We have something in mind. There's some reason we're doing it. It's why we don't think of ourselves as just moving from location to location We have intentions, and we have, maybe we have beliefs and desires. I mean, if you want to divide up the thoughts and the the structures, or the abstract structures that make up the mind of a given person or intelligence, you can say that there are things that are there inside us which cause us to move, that are not there inside rocks, and rocks move for other reasons. Most of us will agree, not all of us, and not perhaps strictly, but most of us will agree that we don't move for the same reasons that rocks move. We travel here and there. We go see things for reasons. Rocks go where nature tells them to go. Now, you might say, no, strictly speaking, if you don't believe in fairy dust or other things that can't be tested, then maybe we are just bouncing around in a more complicated way. We're not going there right now, okay? Just leave that alone. That's a philosophy, ontology, epistemology sort of question that we're not going to deal with right now. Let's just say that there are things going on in our minds that lead us to travel. We have reasons, we have motivations. Dumb things don't have that. Natural intelligences have that. Now, we can say, it's not all natural intelligences that have these special things inside them, like intentions or goals or desires that lead them to move, to travel. Because, dogs don't have goals, do they? Honeybees, blue jays, well, okay. So there's an open question in the world of what's called comparative psychology, or comparative cognition, or comparative whatever brain study, comparative brain and mind studiness, about whether creatures other than ourselves, animals and insects, whether they can do mental time travel. Obviously, none of us can do physical time travel yet. There are physics theories that suggest it's possible, but obviously, go watch a Discovery Channel documentary about that if you want to be introduced, or you can read a book. There are good books on it as well. We'll leave that aside. Mental time travel. Can animals do it? Can birds and bees do it? Well, because we can do it, right? Obviously, we can do it. In some sense of the word, we're doing mental time travel when we. Okay, do you know about the marshmallow test? Listen, you can read a whole book about it, and I did, and then I heard later that the results can't be reproduced, and oh man, I'm gonna have to cite all this in the notes now. This is okay. We're keeping this. Okay, so anyway, the gist of it, from what I distantly remember, is that the results couldn't be reproduced because, but a hypothesis that might explain the marshmallow test better than the skill of sort of deferred gratification is the hypothesis that that at least it requires a prerequisite in the subject being studied, that they actually have sort of how should I say this, that they trust the world, that they haven't been burned. You test a 5-year-old or a 7-year-old. I don't remember when they start doing the marshmallow test. I haven't said what that is. The marshmallow test is where you tell a kid that you can eat this marshmallow right now, or you can have 2 of them in 5 minutes or 10 minutes or 15 minutes or whatever, see how far you can go. And kids can't do it at a certain age, and then they suddenly can. And then, it predicts, the idea went, it predicts a lot about your future and your success and your adjustedness or potential for adjustedness to the world. Are you going to be well adjusted or poorly adjusted? Are you going to be, financially and otherwise successful, blah, blah, blah. And then later I heard, don't quote me on this, but I heard that it was one of the big pile of studies that couldn't be reproduced in the psychological sciences because it wasn't done well. They didn't use Feynman's rules for how to check things, i.e. do science. Okay, and then I heard somewhere else that I'm going to have to dig up now because I'm talking about it, that that if kids had been burned, if they had been promised things in the years prior to running the experiment, and then they hadn't, and things had fallen through for them from parents who couldn't provide or wouldn't provide, or friends or teachers or whatever, that they would fail the marshmallow test. You couldn't nearly as easily convince them to wait for that second marshmallow because they didn't think it was coming. A digression. Okay, I didn't mean to talk about that. The point is mental time travel, and we do it when we say wait for a marshmallow because we think we know somehow we comprehend that in the future if I do this thing or not do this thing, I don't eat this marshmallow in the future, there will be 2 marshmallows available to me, and the eating will be stupendous. Okay. And we travel back in time. I remember the last time I took the marshmallow test, that guy really did bring out 2 marshmallows, and the other kids got to eat 2 marshmallows, and I only had the one, and I didn't get to eat any when they got to eat their 2, because I had already eaten my one, and it didn't taste that good because it wasn't 2. And okay, so we travel back in time to get that information. Well, you can say we travel forward or backward in time, and you can ask the question as psychologists, comparative psychologists do, or you can ask the question, do animals do it, or which animals do it? How do you know? All these wonderful questions. But you're not just talking about time. I mean, time and space, you can't separate them. I'm not traveling forward in time to the marshmallow time, the 2 marshmallow time, without the space with it. I mean, where is the marshmallow time? Or where are the 2 marshmallows? They are in presumably the space where you're sitting doing the experiment, but then it extends to things like savings accounts. If you put away a few percent of your income every month, you travel forward in time. You don't just look at one part of it. In the future, abstractly, I will have a pile of money. It's like, no, I will have a pile of money, and I will be living in this place, either where I am now or where I want to live, etc. Traveling forward and backward in time entails traveling forward and backward in space. And of course, we're talking mentally, not physically. We don't have much to say about actual physical time travel. Not today, anyway. Okay. What about space and time? It's worth dwelling on them, whether or not you're traveling or just moving, whether or not you're naturally intelligent or just rock-like. We can just briefly say that they are, like everything, bizarre and strange and counterintuitive or unintuitive or unfamiliar or not the way they seem to us. Let's just leave it at that. Let's not go there. Just put a placeholder in your mind that space and time, we've talked a little bit about this already, we'll talk a lot about it later. Space and time, the real space and time, not we can say models or representations or whatever is in your head when you're supposedly traveling forward and backward in space and time. The real space and time are far more strange than than they seem to us, and we don't have a really persuasive way of explaining why that is. See, I mean, it's hard to talk about. It's hard to talk because I'm desperately trying not to talk about quantum theory and relativity, because then it's like there must be some rule where as soon as you start talking about that, you're like, what are you talking about? You're supposed to be talking about travel and natural intelligence, and then you find yourself talking about quarks and entanglement. And the problem, of course, is that every conversation can collapse, no pun intended, collapse the waveform. Every conversation can collapse into discussion of such bizarre quantum things, and of course everything's made of these things, and we're all in the relative space-time continuum that they say we are, if it's true, blah, blah, blah. Okay, I'm not writing anything about that. The show notes will have nothing about that or nothing of substance, because we're not here to talk about that. What about mental versus physical travel? Okay, so we're smartish. We have smartish stuff coming out of our brains. We're naturally intelligent. Even the dumbest amongst us is very naturally intelligent compared to a rock or compared to an amoeba. And the amoeba might be intelligent depending on how you define it. It's if you say that reflexive automaton-like behavior does not betray intelligence, well, then you have to find a cutoff point. At what point in complexity between amoeba and orangutan or amoeba and your neighbor is the point where intelligence starts? That's a difficult cutoff point to decide, and it is a decision. We've already mentioned that O'Shea and Bertrand Russell both make the point far apart in space and time that there is no gap. There's no wide gap between the continuum of, or it's not a continuum, but the creatures from humble to human. There's no wide gap in how they think or in how they're constructed. Whether that's the neurons, there are essentially no differences between neurons of simple creatures and complex creatures, according to O'Shea. And then, of course, at least externally, as Russell points out many years ago, we all seem like we're on a very smooth curve. The gaps between creatures, however you want to order them, are not big. And if it's true of their physical condition, it's probably true of their mental condition as well. Okay, so if we're not going to, let's just draw the line between rocks and amoebas and leave it at that. We're mentally time traveling in a certain sense. We are physically moving around and traveling, as everything is. And, all right, so if we're really interested in natural intelligence, we have to have a sense of just how sort of profound it is. And in order to be impressed by it, we have to look at it more closely. It's like what? It's like nothing. Intelligence is like nothing in the universe. And that's the problem. That's why it's so close to us. We are it in a sense, and yet it's so far away because it's the most difficult thing to understand because it's so complex. Jeff Hinton is sort of like arguably one of the godfathers or the godfather of deep learning in the field of artificial intelligence. We're not going to talk about deep learning. We're going to talk about his epiphany that led him to switch fields during university and stop studying psychology or studying in the psychology department and move on to things that eventually led him to make pioneering progress in the field of artificial intelligence. So he's at Cambridge and he's doing psychology experiments on kids. And the basic hypothesis was that kids go from it's sort of Piaget style stuff. There's a phase that defines when kids are more interested in color, and then as they get older, they move into a phase that defines when kids are more interested in shapes. And he's testing this 5-year-old kid. He's tested a few of them, and they kind of do what he predicts they're going to do. You have to train the kids to sort of notice a pattern. Okay, it's triangle, triangle, square. Okay, which one doesn't belong? The square doesn't belong. They're all the same color. Triangle, triangle, circle. Okay, the circle doesn't belong. And then you say, okay, 3 triangles, 2 of them are red, 1 of them's blue. Which one doesn't belong? And then, of course, the blue one doesn't belong. And then what do you do when you mix the two? Well, you mix the two. The reason you do it is because you want to find out whether a particular subject or a particular kid is more interested, paying more attention to shapes or paying more attention to colors. But what happened with Hinton's, one of his subjects, is he when he was asked the question, he responded. He said, "You've painted that one the wrong color." Okay, so whatever, right? You've painted that one the wrong color. Well, that actually blew the mind of Jeff Hinton because it forced him to realize that this kid had done something fantastically complex at the age of 5 for which his models, psychological models that he had inherited and perhaps slightly tweaked or adopted in his studies from psychology, from the discipline of psychology, those models could not even touch what this kid just did. Okay, this is how Hinton explains it. The model that I was trying to corroborate was a very dumb, vague model that said, when you're little, children attend more to color, and as they get bigger, they attend more to shape. It's an incredibly primitive model that doesn't say how anything works. It's just a slight change in emphasis from color to shape. Then I was confronted by this kid who looks at them and says, "You've painted that one the wrong color." Here's an information processing system, by which he means the kid. Here's an information processing system that has learned what the task is from the training examples, and because he thinks there should be an odd one out, he realizes there isn't a single odd one out, and that I must have made a mistake, and the mistake was probably that I painted that one the wrong color. Nothing in the model of children that I was testing allowed for that level of complexity at all. This was hugely more complex than any of the models in psychology. It was an information processing system that was smart and could figure out what was going on, and for me, that was the end of psychology. The models they had were hopelessly inadequate compared with the complexity of what they were dealing with. That's natural intelligence. You've painted that one the wrong color. What does this kid have to do? This kid has to travel in space and time to figure that out, to figure out what's going on. Okay? He's got to have some sort of representation. They tend to use that term in psychology and in artificial intelligence. Some sort of representation of the person doing the test, the pattern that person is intending to put forth in front of the child. And they have to then perceive that there's something wrong. Then they have to come up with a guess. We've talked about guessing. A guess about what led to this break in the pattern. And then that guess has to be the right answer, or a plausible answer. And then they have to put it back to they have to go to different places in time and space around the situation that they're in now, mentally travel to figure all that stuff out. This is a big part of what it means to be naturally intelligent. Now you can argue that, and some comparative psychologists do argue this, that animals, any animals or creatures lesser than humans can't do this sort of mental time travel. They're trapped in time is the phrase that you'll hear if you read a little bit about this stuff. Trapped in time are creatures lesser than humans. And why? Well, because when they're young, they start exhibiting nesting behavior or something similar that looks like what humans do when they're thinking about the future and time traveling, but they're not really doing it because they haven't had time to learn anything, these animals. It's just instinct, it's reflex, it's something that's less than what we're doing because they haven't had time to learn it. Well, we just talked yesterday about how learning might need a demotion in its role as part of the important suite of things related to intelligence. Maybe. If we take that off the table, if we and any other reasons that might come up, let's say we can take them off the table, why other creatures are not doing this time traveling, then it's an essential feature. Time and space travel, mental time and space travel, as we're calling it, is an essential feature of natural intelligence. Whatever we mean by that, however we would define it rigorously. How would you run these experiments? People are working on these things. They're not necessarily working on them in the way that what we're saying here suggests, because there are a lot of assumptions baked into the culture around whether or not whether the experimenters that are running these things, the professionals, which of course we are not here at Retrace. So another brick of salt to be taken with these ideas. Travel, guessing, checking, which ones learning, which ones are really part of what natural intelligence is about. Do you know? Can you armchair this one? Shooting from the hip, do you hit the target? I don't think so. This is complicated stuff. It's not obvious, and you shouldn't think it's obvious. But think about travel when you think about natural intelligence. All right. Amendments and corrections from our last segment, Re11. I was so excited about all the stuff, and then I forgot to say, and I had written down Feynman's 3 rules for checking crazy ideas, i.e. doing science or doing the equivalent of science. He has 3 rules. I wrote them down. I skipped over them in my notes. Okay. My bad. Here they are. Number 1, bend over backwards to report everything you find. This is in order to help others see the value of your idea checking work, your science. You have to bend over backwards. That's not necessarily taken for granted. I mean, we can't run the experiment, but it's arguable. Feynman certainly thought at the time of his talk in the 70s that this is not normal. We're supposed to be normally doing this. We're scientists. We're getting paid to do this. We're supposed to be these people, and we're not bending over backwards. It's the exception, not the rule, to bend over backwards to report everything. You can't make your report dependent on the outcome. You have to report the work, not just the outcomes that you like or the outcomes that will advance your career. And yet, we can see why people might be, have perverse incentives. Rule number 1, bend over backwards. Rule number 2, don't fool yourself. Don't fool yourself, idiot. You're the easiest one to fool. You want the cool result to be what you get. You want to have had that brilliant moment. You can always be sure that someone's talking about someone's excited, let's say, about an idea when they say it came to them in a dream, or they were staring off at something, or some moment where didn't I see that in the movie? Yes, you did see it in the movie. Now you're trying to be in the movie. I don't care where the idea came from. I don't care how cool it is. Did you check it? If you didn't check it, it might be crazy. It might be useless. You don't know. You can't tell me because you fooled yourself. Don't fool yourself. You're the easiest one to fool. And by the way, if you don't fool yourself, then it'll be much easier not to fool your fellow checkers, your colleagues, your peers, whoever else is working on this stuff, whomever else. You just be honest, okay? Don't fool yourself. Report everything. Bend over backwards to report everything and be honest, and you'll be fine. Don't do all those things. Your reputation is probably, eventually going to crumble. It might not happen until after you're long gone, but that should still matter to you. Rule number 3. Rule number 1, bend over backwards. Rule number 2, don't fool yourself. Rule number 3, don't fool outsiders. Don't fool me. If I don't know about the particle collider or the comparative psychology rat experiments or blue jay experiments, don't tell me about it. Like, don't try and lead me to think that you're more important than you are by selectively telling me what's going on. I think you're important. I'm listening to you. I'm not going to listen more to you. Maybe I will, but I shouldn't listen more to you at this cocktail party that we're at if you seem to be on the verge of greatness. I mean, right, you got to self-promote. Okay. But you've also got to you got to have integrity. That's what Feynman says. It's a matter of integrity. You got to have integrity. And if you don't, well, then you don't have integrity. Plenty of people get away without it, or fool people into thinking they have it when they don't. But don't be one of them. Don't be a bad guy. Be a good guy. All right, those are Feynman's 3 rules. I also said, this is cool, I also said that Darwin delayed publication because he was afraid. He was scared of the trouble he was going to get into if he published his... Well, that looks like it might not have been true. One of his biographers, a scholar who... Oh, gosh, anyway, it's in the show notes of Re11, but I don't have his name in front of me. It was about 2007 or so. His recent work on scholarly work on Darwin leads to ample evidence. He says that Darwin was just busy. He was just busy, and he was doing his homework on evolution. He was doing his homework on several other things. He was getting sick every once in a while. He was just busy. It took him a long time to get around to publishing it. Now, maybe his biographer is biased, but nonetheless, this is out there as an idea that he wasn't scared. He was a true scientist, fearless, assuming that fearlessness is part of being a true scientist, and it wasn't the fear that kept him from publishing. And then he co-published with Wallace the first paper on the subject when he realized that Wallace was. So now that came from checking. I'm making this correction, this noble correction, because I checked what I said. Like, I said this thing, I believed it, and then you got to make sure. So I go to, got to put in the notes. You got to cite a source. You say something like that, you got to cite a source. I was in the encyclopedia, the kids' encyclopedia. I was in all these books I've got. None of them were telling me. I was like, where did I hear this? I'm gonna have to. What am I gonna? I don't want to cite a web page. Those things. They're like fireworks, they're just there and gone. And eventually I found a good scholarly article that corrected me, and that also reinforced or supported my previous thought that he had not published because he was afraid. It just recapped it and then said it's not true. Okay. Amendments and corrections concluded. This is Retrace, RETRAICE.com, RETRAICE.com. Segment number 11, signing off.